Welcome back to another episode on the Experts Network. When it comes to shortcut liquid recovery using propane refrigeration, there's a very small piece of equipment that is often overlooked but plays a very critical role. What is it? Your spray nozzle. Often these nozzles have years of use without ever being looked at. With this lack of attention, it leads operations to sometimes adding methanol to try to combat the hydrates that are forming across the multiple exchangers used in the system. And this is due to a lack of performance from the nozzles. Maybe you're saying, I didn't know these nozzles could go bad, or is the original nozzle even the correct one for our system? Finally, we hear a lot of, we just inject the maximum amount of glycol so we don't have to worry about the hydrates. Well, today I'm going to explain why and what goes into selecting the nozzle for your application. Stay tuned.
Welcome to the Experts Network.
Hi, my name is Drew Gibson. I'm a process specialist here at Dehydration Experts. Now, if you haven't seen it already or you want to refresh yourself with the EG-Refrigeration process system, I recommend going back and watching my previous video, EG-Refrigeration versus TG dehydration. But today we're going to focus on just the EG-Refrigeration, and in particular, the glycol injection nozzles. So where do we start off? Well, first things first, we need to know how many nozzles we have and where they're situated within the system. So here we can see the three locations circled in yellow, where the nozzles are typically located. And this will be at the gas-to-gas exchanger, the gas-to-liquid exchanger, and chiller. For this example today, I'm just going to use one nozzle at each location. However, there are systems that use multiple nozzles, but everything is dependent on the size and the configuration. So now that we know the quantity and location, we require the operating conditions for the gas process stream. These conditions are key to making sure we select the correct nozzle. So we need to know the gas composition, we need to know pressures in this system, temperature in and out of the various exchangers, we need to know the gas process flow rate, and the lean enriched glycol weight percentage along with the specific gravity of the glycol. Now, with this information, it allows us to determine the saturated water content of the gas in each stage of the process. We can now complete the calculations which will determine the required ethylene glycol injection rate at each nozzle. But what we're going to notice here is the majority of the overall ethylene glycol injection flow is going to happen at the first exchanger, the gas-to-gas. This is also where the most water is condensed out of the gas stream. This is due to the logarithmic scale for water holding capacity of natural gas. Just knowing the amount of flow to each nozzle location isn't enough. How it's mixed into the process stream is also critical. We need to know EG. We need to know that the EG is being injected correctly and just not by some homemade nozzle. So it is crucial that the ethylene glycol is atomized as much as possible and dispersed evenly across the tube sheet in the exchangers. When we talk about atomization of the EG water mixture, we're talking about droplet size. A few things that can determine droplet size are the glycol properties, the capacity of the nozzle, the spraying pressure and angle. So how small of a droplet are we talking? Well, anywhere from a light rain to a fog. Here we can see the micron size for heavy, moderate, and light rain along with fog. And this is thanks to the folks at Spraying Systems Company for providing this. Now for a more visual comparison, we can see in this picture where the various rainfall droplet size would be in relation to micron size. Remember, we're shooting for a fog-sized droplet, which is between 10 to 100 micron. Now that's pretty small. Since the visibility threshold of the naked human eye is about 40 micron, a human hair is around 70 micron. Now when we're looking at light rain, that is between 100 to 500 microns in size, and that's comparable to having table salt, which is close to 120 microns. And well, let's just lump in moderate and heavy rain together, and that's comparable to the size of beach sand at around 2,000 micron size. So the smaller the droplet size, the EG water mixture, the better. We're not so much directly spraying the glycol into the tubes, but we're actually allowing the process stream to carry it into the tubes. With the water vapor condensing in every tube in the exchangers, it's absolutely vital that the glycol also enters every single tube, or the condensed water will freeze when the temperature drops below the hydrate point of the gas. Remember my first video, the ethylene glycol injected in this process does not absorb the water vapor from the gas. Instead, it forms an antifreeze mixture when blended with the condensed water. The video showing here is an example of the full cone spray, and it's in the vertical plane. Notice the larger droplet size and how those droplets are bouncing off the surface, along with the random flow coverage. So how is the full cone going to perform when spraying in a horizontal plane and at the tube sheet? Well, it's going to be the same, if not worse. What we want to avoid happening is the random flow coverage across the tube sheet face, the spray droplets bouncing off the tube sheet face, and we don't want to collect liquid on the lower portion of the tube sheet. Now I just played this video, but I want to show the huge difference between the fine spray nozzle and the smaller droplet size compared to the full cone. Notice the rebound effect of the droplets is a lot less dramatic. The flow coverage is distributed more evenly than the full cone nozzle. And with this, the droplets tend to stay in the direction of flow much easier. These three characteristics, along with having less of a gravity effect on the droplets, all results in a more effective and efficient performing system. So from the calculations completed based on the information of the gas composition, the pressures, temperature in and out of the various exchangers, the process gas flow rate, lean and rich glycol weight percentage, and the glycol specific gravity, we can see the injection rates with the safety factor included are 2.45 liters per minute at the gas to gas. It's 0.17 liters per minute at the gas to liquid, and the chiller is at 0.02 liters per minute. So now we need to know the dimensional information before we can look at the nozzle selection chart. For this, we'll need to know the diameter of the tube sheet, which is D1, along with the distance the nozzle is away from the tube sheet, L1. You can calculate the required spray angle, which is A1, to cover the whole tube sheet. For this example, we'll consider that the distance of L1 is 25 centimeters, which is the distance the nozzle is away from the tube sheet. And the diameter of the tube sheet is 40 centimeters. That's going to give us a 77-degree spray angle. Word of caution though, most of you may not be able to find this information in your plant books. So it's a great idea to take out a tape measure and record these distances during either a turnaround or startup, especially the distance between the nozzle tip and the tube sheet. Now we can start the process of looking through the nozzle selection charts. For this example, we're going to use the Uni-Jet tip type D with a 1/4 inch NPT connection. Starting from the left hand side of the chart, we see the connection size first, right? We already said that's 1/4 inch. Then moving to the top of the chart, we see the tip type, and that's D. We generally like to keep the pressure differential across the nozzle at 6 bar. So under the flow capacity, we'll see the 6 bar column. Moving down about three quarters of the way, we see 2.5, which is close to the required 2.45 liters per minute for the gas to gas exchanger. Moving across that row all the way to the right hand side, we'll see the spray angle for the 6 bar differential pressure, which is at 89 degrees. Now, keep in mind the actual spray angle of the nozzle may be less than the theoretical coverage area, because gravity will cause the original spray angle to shrink as the droplets flow from the nozzle tip to the tube sheet. This is especially true for full cone nozzles or nozzles that do not form a fine enough mist because of wear and tear over continued use. Now, the calculated required angle was 77 degrees. The selected nozzle would provide us with a reasonable operational range of 79 to 89 degrees. Most spray characteristics like spray angles provided are based on that of water. So liquids like EG water mixture with different characteristics tend to form a relatively smaller spray angle compared to just water. This is also dependent on viscosity, nozzle capacity, and spraying pressure. So having a slightly larger spray angle allows us a flexibility once these nozzles are placed into operation. Hopefully this provides you the starting point to help you select the correct nozzles for your operating conditions. There's a lot more to cover relating to nozzles, like materials, placement, liquid temperatures, retractable systems, filtration. So if you have any questions, comment below, or you can contact us directly. Thanks again for watching our YouTube channel, and please subscribe so you won't miss any more exciting and informative episodes. Click that bell to get notified on new videos.